Welcome back, everybody. I don't want to give a quiz today, so we're not having a quiz today. Uh, Made you look, right? Um, I have been in misery the last week and a half because of these allergies. So, um, also felt like I don't have nothing to grade. But we will still keep the number of quizzes dropped, so nothing changes there. Um, And you might have noticed that I did not send out a worksheet or guided lecture notes for that one. I've decided to drop it from the semester. It's not going to be needed for the final exam, so we're not going to do it. I just did not have enough time to make it. But there was another thing that I wanted to do that was I felt like more important. So I actually added a page to the notes, which we'll get to in a second. And then the rest of the time will basically be review to just get some more practice with radiuses and intervals of convergence, along with identifying centers, integrating and differentiating, and all that jazz. So one minor thing that I did want to go over these problems that we went that I sent out the worksheet the that page uh, after class on Thursday. So with this first one, the problem is in order to write it as a true power series, it needs to be in the form of x minus x sub 0 or x naught to the n. But this one has 3x plus 4 to the n over 5n. So we need to first factor out a 3. And by doing that, we get 3 times x plus 4 thirds to the n, which can then, the n can be distributed because it's multiplication. And so we've got 3 to the n over 5 to the 5n times x plus 4 thirds n. And I decided to use the root test. The ratio test would do just as well for this one. It's just the root test seemed easier. It takes less time to write mainly, but the ratio test would also work just fine. And so we end up with 3 to the n to the 1 over n just becomes 3x plus 4 thirds to the n becomes just absolute value of x plus 4 thirds. And then the 5n to the 1 over n, it makes more sense to look at it as the nth root of 5 to the 5n. Now, the nth root of any number is always going to go to 1 as n approaches a positive infinity. And actually, we also have the other special limit that the nth root of n goes to 1. So that whole thing will go to 1, meaning we just have 3 times the absolute value of x plus 4 thirds is less than 1, which we need to solve. So we divide by 3. And that gives us our radius of convergence with our center at negative 4 thirds. So we utilize that to find the open interval of convergence by subtracting 4 thirds from both sides. We get that. And then in order to find the interval of convergence, we need to see whether or not the endpoints can be included. At negative 5 thirds, when you plug that in, negative 5 thirds plus 4 thirds is negative 1 third to the n. That cancels out the 3 n's, leaving us with just negative 1 to the n over 5 to the n, or 5n, which is convergent because it is a decreasing sequence in which its limit of everything except for the negative 1 over n part does go to 0, and all those terms are positive, meaning that it converges by the alternating series test. But if you plug in negative 1, you get 1 third to the n, which cancels out the 3 to the n, giving us 1 over 5 to the n, which is technically the harmonic series. It's 1/5 of the harmonic series, but 1/5 of infinity is still infinity. So it's divergent, meaning we can include the left endpoint, but we cannot include the right endpoint, giving us our final answer of 1/3 for its radius convergence, and its interval of convergence is as such. Any questions? Now, an interesting one is this one here, because instead of it being x minus 4 to the k, it's x minus 4 to the 2k, which can happen every once in a while. So this one, it only has even powers of its variables. So the thing is, it doesn't matter what you do, it's still going to do the same, like still be solved the same way. I decided to use the the root test, but the ratio test would work just as well here. Um, and when we do that, we get absolute value of x minus 4 when we take the limit as k approaches infinity, that is. Absolute value of x minus 4, technically squared, but it really doesn't actually even matter at this point because it's going to be always positive because it's squared. And then over 9, you multiply both sides by 9 to get the x minus 4 by itself, but it's squared. So we have to take the square root of both sides. And technically speaking, we put the plus or minus but it's not really necessary when we're solving this inequality. And so we get this. So the radius of convergence is 3. So solving for the open interval of convergence, we get 1 to 7. Then we test the endpoints, but both of them end up being 1. So it's divergent at both of them. So it cannot be included. Are there any questions on that? Okay. Next, back on to the power series stuff. So we left off with this question right here. The thing that we need to notice, especially when it says power series, like find a power series representation of this function. If it is a geometric series or a series that is a known series, we can utilize that to our advantage. But if not, then we need to look at it and see whether or not we can represent it by one of those series, in relation to one of those series, rather. So P of x is natural log of x plus 1. If you take the derivative of that, you get 1 over 1 plus x, which is 1 over 1 minus negative x, to get it into the geometric series form. So if we find the geometric series for 1 over 1 minus negative x and integrate it, we will get the power series for P of x. And that's what I did down below. I rewrote it as a geometric series, and we've got that. So the integral let's also realize that the radius of convergence is equal to 1. You can verify that on your own time if you'd like to, but it's pretty cut and dry. You just need to take the root test, and you'll see that the radius convergence is 1. And because I don't necessarily, and it's center, and center equals 0. Because I'm only asked to find the interval of convergence of P of x, I don't need to bother finding its interval of convergence. So natural log of x plus 1 is equal to the integral of 1 over 1 minus negative x dx, which is equal to the sum from k equals 0 to infinity of the integral of negative 1 to the k x to the k dx. That's what we have. The integral of that function. So if we find this, we get our answer. And as the theorem says, is provided we are within the radius of convergence. The reason why I can do this is because we're within the radius of convergence. Otherwise, this integral, this summation would have to be inside. But because we are within the radius of convergence, we can bring the integration onto the inside and integrate this term by term. So that becomes C plus the sum from k equals 0 to, or was it k? Yeah, k equals 0 to infinity of negative 1 to the k over k plus 1 times x to the k plus 1. But what's C? Does anybody have questions so far? So the negative 1 to the k, it doesn't depend upon x. It's just a constant for each individual k. And then x to the k for each k, the integral of that by the power rule of integration is x to the k plus 1 over k plus 1. So we have that. Are there any questions on that? So the question then becomes, what is C? If only there was a nice number that I could plug into natural log of x plus 1 to find an initial condition. Note, P of 0 equals natural log of 1, which is equal to 0. This is an initial condition. That we can utilize to solve for C. The reason why I'm choosing 0, by the way, instead of anything else, is that if I plug in 0 for x, all of this goes away. Because it'll be 0 to the power of anything, which will always be 0. And that allows me to wipe that entire thing out. If I try to do so just to show you how you have to be a little bit clever and careful with these things, sure, I could use the fact that P of 1, write this in pink. Don't write this. I'm writing it in pink. P of 1 is natural log of 2. And I could use that to solve for C, but the problem is, if I do this, C plus, well, actually, we can't actually include one. No, one is included. C plus the sum from k equals 0 to infinity of -1 to the k over k plus 1 times 1 to the k plus 1. But 1 to the k plus 1 is just 1. And the question is, what is this? Do you guys know? I don't even remember what it is. I know it's the alternating series. It's the alternating harmonic series, and it is convergent by the alternating series. But what it equals, not a good actually, it equals natural log of 2. Huh. Fun. But we'll find out in a second why that's true. So yeah, the alternating series converges to natural log of 2. The alternating harmonic series, excuse me. But the problem is, right at this moment, I have no clue what this equals, so I can't use this to solve for C. With 0, I am able to plug it in and find a specific value. So, utilizing this, I have that C plus the sum from k equals 0 to infinity of -1 to the k over k plus 1 times 0 to the k plus 1, which equals C plus 0, must equal 0. So C is equal to 0. That's not always guaranteed. A lot of the times it does happen that the constant ends up being 0, but that's not guaranteed. So we do need to actually sit down and verify it. It just so happens that a lot of times it is. So P of x, which is equal to the natural log of x plus 1, did I write it as x plus 1? Yeah. Is equal to the series from k equals 0 to infinity of -1 to the k over k plus 1 times x to the k plus 1, which we could re-index if we wanted to make it prettier. We could bring the index up by 1, which would bring down the indices inside the sequence by 1 to make it look a little prettier, but it's not required. Any questions on that? That is the first part of this problem. Nothing? Okay, now we need to find the intervals of convergence, the interval of convergence. Since the sum, since 1 over 1 plus x has ROC equal to 1, so does P. So that means the absolute value of x is less than 1, which means that we have -1 less than x less than 1. But we still need to test the endpoints. That gives me the open interval of convergence, not the full interval of convergence. So at x equals -1, we get the sum from k equals 0 to infinity of 1 over k plus 1. Make sure you understand how I got that. Because when I plug in -1, I'm going to get -1 to the k, or it's going to be, sorry, -1, specifically just a -1. Because when I plug in -1, I'm going to get -1 to the k times the -1 to the k plus 1. That's really -1 to the 2k times a -1. Let me write that out just so you can see it in action. You're going to get this. But this right here combines to a -1 to the 2k times a -1. And this is just equal to 1. So you just get -1 over k plus 1, which is the harmonic series. So divergent by the p-test. With limit comparison of 1 over k. I mean, actually, you don't even really need to. You can reset it to index 1, and you'll see that it is, in fact, the harmonic series. So it's divergent. Any questions on that? All right. So at x equals 1, we get the series from k equals 0 to infinity of 1 over k plus 1. -1 to the k. And that is convergent by alt series. So the interval of convergence does not include the left endpoint, but it does include the right endpoint. So what this tells us is that the derivative, the function natural log of x plus 1 is equal to that series, provided we are within this range. So we now know a formula for natural log of, we know a series, excuse me, for natural log of 0.5, for natural log of 0.75, for natural log of 1, for natural log of 2. We can find those things by plugging in random x's between -1 and 1, and we can find power series representations of natural log. Any questions on that? Okay. So we will do the challenge problem in a second, but I want to do another one of these situations that involves integrating and differentiation first. Find a power series representation of tangent inverse of x and find its center and interval of convergence. What do you think you should do? What do you notice about tangent inverse of x? Because there's no known series that we know of for this one. Maybe if it was like a way, like if it was tangent of x, I haven't given it yet, but tangent, the power series for sine and cosine, I can give them to you, and so you could might do the division, but that wouldn't really help. Is there anything you might notice about tangent inverse? Yes. F prime of x is equal to 1 over 1 plus x squared, which is equal to 1 over 1 minus negative x squared. Oh, no, it's not. 1 minus the quantity negative x squared, like that. Okay. And key observation, so that means that if we find a power series representation for this, we can integrate that and we will get tangent inverse. So sometimes we need to integrate, sometimes we need to differentiate. It all depends on the situation. Key observation number 2, all right, so this means if we find this power series and integrate, we find tangent inverse of x's. That's what that means. Now that we know that there is a way to represent tangent inverse's derivative as a power series, we can integrate that power series and get up to tangent inverse. Okay? So the key observation number 2 is that 1 over 1 minus negative x squared, this is our box right here. So in the geometric series known representation, that's going to become the series, the infinite sum from k equals 0 to infinity of negative x squared to the k, which is equal to the sum from k equals 0 to infinity of -1 to the k, x to the 2k. Any questions on that? All right, go ahead and integrate it term by term. You should do it yourself. I'll slowly fill in details. And integration rarely, if ever, changes the indices lower bound. So you can just assume that it's going to be k equals 0. It's very, very unlikely that it changes. Should have put the C in front because otherwise it looks like it's part of the series, but it's not. It's an outside constant. It's not part of the summation. So you should get -1 to the k over 2k plus 1 times x to the 2k plus 1. Are there any questions on that? Okay, but what's the constant? So we know that the radius of convergence, by the way, this thing has an ROC equal to 1, which means that the absolute value of x needs to be between -1 and 1. So I can't necessarily use -1 or +1 yet because I don't necessarily know if it converges on those endpoints. It could. The first one doesn't. This one has an interval of convergence of just parenthesis -1 to +1. That's it. So it might make sense to plug in 0. That would be a nice thing. So note f of 0 equals tangent inverse of 0, which is equal to what value of theta makes tangent equal to 0? Tangent theta equal to 0. Or you can use your calculator like a chump. Kidding. I just have it memorized because I've been doing this for so long. Tangent inverse of 0 is 0. So this means that we have the sum from k equals 0 to infinity. So remember, tangent, sine over cosine. The only time sine equals 0 is at 0 or any multiple of pi. But tangent inverse's domain, or sorry, range, is between -pi/2 and pi/2. So it's going to be 0. But it could technically, if you want to shift it up or something like that, it could be pi or 2 pi or whatever. Either way. So that's going to be -1 to the k over 2k plus 1 times 0 to the 2k plus 1 plus a constant c is equal to 0. That gives me c is equal to 0. So now we have a power series representation of tangent inverse, which is pretty cool if you ask me. That's a pretty awesome result that we get for frizzles, basically. So f of x, which is equal to tangent inverse of x, is equal to the series from k equals 0 to infinity of -1 to the k over 2k plus 1 times x to the 2k plus 1. We need to still find its interval of convergence and its center. Well, we already know where its center is. I forgot to mention that from up here. The center is at 0 because it's just x to the 2k plus x to the 2k. And same thing for that because it's x minus 0 technically. Okay? We still need to find the interval of convergence. So absolute value of x needs to be less than 1, which means -1 less than x less than 1. And I want you to determine the interval of convergence by testing the endpoints. That's the open interval of convergence, parenthesis -1 to +1. But we should also know whether or not it converges or diverges at the endpoints. And just because every single other time it's always been that like one of them converges and one of them diverges, that's not always the case, as we see here. And then as a little reminder from last time, when you differentiate, so the integral, the derivative, and the function all have the same radius of convergence. And in fact, that's true in general. The second integral, the second derivative, third integral, third derivative, and so on and so forth, they always have the same radius of convergence, but the interval of convergence changes. Can change, not necessarily. And typically speaking, when you take derivatives, it makes it less stable. So the interval of convergence typically shrinks when you take derivatives, but it usually becomes more stable when you integrate. So the interval of convergence of an integration usually is a little bit bigger. Not always a little bit bigger. It can be the same, but more often than not, it's a little bit bigger. This is what we get for the left endpoint. Because when you plug in -1 into it, you get -1 to the 2k, which is an even power on a -1. That becomes 1, and then an additional -1 on top. That's why it's -1 to the k plus 1. Does everyone see that? It's okay if you don't. But I won't know if you don't understand it unless you speak up. And that is convergent by the alternating series test. And then we'll try x equals 1, but that actually ends up giving me the exact same series. Well, not exactly the same. It's the negative version of the previous one. Because when you plug in 1, 2k to 1 to the 2k plus 1, that just wipes away. It's gone. So we have -1 to the k, 2k plus 1, which is also convergent by the alternating series test. So the IOC, so here is the power series representation of tangent inverse, and its interval of convergence is bracket -1 to +1 bracket. I don't want to get to the exciting part too soon. This problem is very, very special to me. And it actually has a very, very, it's a very, very important one, actually, surprisingly. So this thing converges at both of its endpoints. That's kind of rare, usually. Usually you get one, but you don't get the other. But this time we did. Okay. Any questions on that? So now we get to have a really, 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 really awesome result. Prove that pi over 4 is equal to 1 minus 1/3 plus 1/5 minus 1/7 plus 1/9 minus 1/11 plus 1/13, and so on and so forth. How do you think we should do it? It obviously has to do with this problem, right? It needs to be something. What do you think you should do? Yes, so specifically, we're going to be working with this series, and we're going to note that tangent inverse of 1 is equal to what? So remember, if you want to learn how to do these ones, fun fact, I don't have these memorized. I don't. I have to think about it every single time in my head. Inverse trig functions, they take an angle and spit out a number. Inverse trig undoes that. It takes a number and spits out an angle, specifically between -pi/2 and pi/2. So what we're really asking when we write this, and this is what I'm thinking in my head every single time I do inverse trig, I don't have it memorized, is tangent of theta equals 1. For what value of theta does tangent equal 1? Pi over 4. So tangent inverse of 1 is equal to pi over 4. Using tangent inverse of x's power series, we have that pi over 4, which equals tangent inverse of 1, is equal to the series from k equals 0 to infinity of -1 to the k over 2k plus 1 times 1 to the 2k plus 1. But 1 to the 2k plus 1 is just 1. And so let's start writing out the terms and see if it lines up. I plug in 0, -1 to the 0 is 1. 2 times 0 plus 1, that's 1. Plug in k equals 1 next. -1 to the 1 is -1. So this is going to be a minus. And then 2 times 1 plus 1, that's 3. So minus 1/3. Plus 1/5. Minus 1/7. Plus ... on forever. And boom, we have proved it. Proof. We get to put a black box at the end and say QED. Why do I care? Why should we care? And I want to kind of push on that for a second and talk about it because I think this is beautiful. Actually, fun fact, my wife and I were talking about this 2 nights ago during our precious free time. This is what we do on an average Friday or Saturday night. Is that what you guys do too, right? With your significant others, you talk about series and sequences and all that jazz. No? Okay, well, weird. You guys are weird, not me. But anyways, so we were talking about this, and I love teaching calculus. And one thing I tell my students now, as it's become far more apparent to me, calculus is the study of 0 and infinity. That's what it is. It really is. It's just how to manipulate infinity and manipulate 0 to your liking. And the one thing I want to push back, and the reason why this is so important to honestly the universe at large, this is just an infinite sum of fractions. And one of the things that you will prove if you ever plan on becoming a math major, you might see, like, does anybody know what this symbol means? I wouldn't expect you to. We know what this is. That's the real numbers. This right here is the rational numbers. It's all fractions, and technically integers are fractions, right? 2 can be written as 2 over 1. But this is 2/3, -5/8, whatever you want. And there's a fact that you will prove if you plan on taking abstract algebra. You might even prove it in topology or in real analysis, that if R and S are in Q, then R plus S is in Q. What that means is that if you take 2 fractions and add them together, you get a fraction. That's just inherently true. And in fact, that can be extrapolated. I can take 10 billion to the 10 billion to the 10 billion numbers of fractions, and I can add them together, and it will always be a fraction. But somewhere along the line, once I include infinity, for whatever reason, even 10 billion to the 10 billion to the 10 billion to the 10 billion, that number of fractions added together will be a fraction. But when I make it infinity, it becomes irrational. So there's something about infinity that changes everything. It goes from being fractions to non-fractions once you incorporate infinity. And I think that is beautiful. I think that is amazing to think about. Something about infinity changes everything that we know, and something that we have to study as human beings to know what it means to be. Mathematics is out there waiting to be discovered for us. It's not something that we had to create ourselves. It is here. And so infinity, despite the fact that we can't really understand it as people, we don't, Like there's a whole thing about human beings and how we gauge infinity. We can't really think past numbers around the trillions. It doesn't make any sense to us. It's why trillionaires can exist and we don't want to burn them at the stake. We should, in my opinion. Nobody deserves to be a trillionaire. That's too much money for any one person. You simply cannot spend it. There is only one entity in this world that can spend $1 trillion, and that's a government because it's in charge of multiple people. But either way, I don't want to get down that rabbit hole any more than that. The fact of the matter is, we have a hard time understanding anything that's bigger than in like trillion, but we have to be able to understand it. And this is a really, really cool fact. Thank you for coming to my TED Talk. I just think this is absolutely gorgeous. This is called the Leibniz representation of pi, if memory serves, and it's a very, very fascinating fact. Okay? So, in short, calculus is the study of how to utilize zero and infinity to your disposal. That's all it is. And what comes with it. Okay, so what time is it? I forgot my watch today. Okay, we still got time before we'll take a break. This one. Find a power series representation of the function y equals 4x minus 7 over 2x squared plus 3x minus 2. Okay, so that does not look like a geometric series. And there isn't much that we could do. One thought that might show up is to say, oh, well, we could complete the square. It's not a bad option. If you complete the square, that does work out a little bit. Because if you complete the square on that, oh, it's not pretty, though. It's not pretty at all. The problem is what you will get is you'll get 1 over number minus, or you'll get 1 over something squared plus or minus 1, or plus or minus a number. And so what we're going to have to do is do a lot of manipulation, but I guarantee you whatever's on the inside here is not going to equal 4x minus 7, which makes this a little bit difficult to write because unlike the previous situation where we had this one right, where was it? Right here, where we already had our center at 0, so we could just multiply the x in and it was all fine and dandy. That's not going to be very, very helpful for us if we have 1 over something squared plus or minus a number, and we have a 4x minus 7 here, not a 1, sorry about that, and I can't bring this inside. That's going to be a problem. So an alternative route is to to decompose it. So decompose. We've got 4x minus 7 over 2x minus 1 times x plus 2 is equal to a over 2x minus 1 plus b over x plus 2. All right. Not too terrible so far. This is good practice. I can't say for certain. We are getting close to the end, right? We have, after this class, 5 more classes together and then the final. And that's it. We're nearing the end. And the final exam is cumulative and it's written by the department. I have no say over what questions go on it. So it could have a question, it could have an integral problem that requires you to do partial fraction decomposition. So this is good practice. What do we do next when it comes to partial fraction decomposition? We got to solve for a and b. So what do I do that we typically don't write? Multiply by the denominators. Savannah is absolutely correct. And that allows us to cancel it over here, and then it gets distributed in. We end up with 4x minus 7 is equal to a times x plus 2 plus b times 2x minus 1. And a lot of students on exam 1 did this, and I want to push back on it and remind you, you can do the term matching. That method does work, but it's much faster to do clever choices of x here because we don't have to deal with any irreducible quadratics that never equals 0. If you can do clever choices of x, do it. It's so much better. So let's do x equals -2. That would give me -8, because it'd be 4 times -2. -8 minus 7, that's -15. The a will go away, because it'll be a times -2 plus 2, goes away. And then I've got b times -5, which gives me b is equal to 3. And then to get rid of the b term and solve for the a term, I need to use x equals 1/2. All right, that would give me 4 times 1/2, that's 2, minus 7, that's -5, equals a times 1/2 plus 2. But 1/2 plus 2 is, well, 2 is 4 halves, plus an additional 1 is 5 halves. So that means that a is equal to -2. Any questions so far? Okay. So now we can write this as two nice fraction pieces. So that means that y is equal to, let's write it with the positive term first. I just like the way it looks better. It actually doesn't matter. -2 over 2x plus 1 plus 3 over x plus 2. Now, both of those things we can write as power series separately. Write each as a power series. So I'm going to do this in stages because I can't work at the same time. Like, it's fine if you are able to do that. If, like, I mean, I can do it if we really want to, but I wouldn't recommend it. That's just too much mental load at one time. So break them down by pieces. So for -2 over 2x plus 1. Well, first and foremost, I need to get that in the form of 1 minus a number. And right now it's pretty okay. Right now it already has the constant term of 1. I just need to rearrange it in such a way that it works out nicely. So this is going to be equal to -2 over 1 plus 2x, which I'm going to rewrite as -2 over 1 minus -2x. It already has the code. Like, so remember, like at the end of the day, going back to the very beginning, don't worry if you haven't finished this, writing this down. We want to get it in the form of 1 over 1 minus a block. That's what we want to do. It already has a constant term that is a 1, so we just need to figure out what the block is. And it's 1 plus 2x right now, so that's actually 1 minus -2x. So we can write this as -2 series from k equals 0 to infinity of -2x to the k, which we can then rewrite perfectly as the sum from k equals 0 to infinity of -1 to the k times 2 to the k plus 1 x to the k. So that thing has a center at 0. So I want to make sure that when I write the power series of that one, I also write it with a center of 0. Think about why that would be the case. So just to show you what the problem is, if I were to say, because there is a clever thing you could do. You could rewrite this x plus 2. You could rewrite this as 3 over 1 plus x plus 1. You could do that. That's fine. That does work. And then I would do, okay, I rewrite this as 1 minus negative parentheses x plus 1. And then I could write it as a series. It would be the sum. It'd be a 3 out here, and it'd be negative x plus 1 to the k. But then they have two different centers. And I can't write them as a singular power series with a singular center. Does that make sense? So I need to also write it with a center at 0. For 3 over x plus 2. Three over 2 plus x. That's good. That's in the proper format-ish. But the problem is it needs to be something like ideally 1 over 1 minus block. So what should I do? How do I get into the proper format? Factor out a 2. That's right. So 3 over, if I factor out a 2, that's what was causing a problem. But by factoring out a 2 from an x that doesn't have a 2, I have to counterbalance that and make it x divided by 2. And that's closer, but that's not perfect because we need it to be 1 over 1 minus blank. So we have to double negate. And what we end up with is 3 halves times 1 over 1 minus parentheses negative x over 2, which is 3 halves sum from k equals 0 to infinity of negative x over 2 to the k, which we can write as the sum from k equals 0 to infinity of negative 1 to the k times 3 over 2 to the k plus 1 x to the k. Any questions so far? Okay. So we have two different power series that are both centered at 0. So that means that y is equal to the sum of negative 1 to the k times 2k plus 1 x to the k from k equals 0 to infinity plus the sum from k equals 0 to infinity of negative 1 to the k times 3 over 2k plus 1 times x to the k. Now, we didn't talk about this because it's usually not very common to deal with until you become a math major, but the question can become, can I combine these? And remember, infinity is a fickle concept. It's very, very strange. As we've seen before, we saw that you can have shapes that have infinite surface area but finite volume. Infinity is weird. We know that for a finite number of a finite summation, if I make this go to n instead, then I can combine them because they start with the same index, so I can combine them all together, and they end with the same index, or the same upper bound. But infinity is strange. Can you add up? Can you bring them together? And the answer is yes, as long as you are within the interval of convergence. So, provided that we are within the interval of convergence, these things are more specifically within the radius of convergence, we can combine them. So y can be written as the sum from k equals 0 to infinity of bracket negative 1 to the k times 2k plus 1 plus negative 1 to the k times 3 over 2 to the k plus 1 times x to the k. Provided within the IOC. Any questions on that? Okay. Now the question then becomes, I mean, I could leave it as is. And there are many different ways to go out finding. So the question, remember, the question asks to find its center and its interval of convergence. So there are two methodologies on how you could probably find the radius of convergence. What would you suggest? If you had to write this on an exam, how would you go about it? I mean, it's always my way, just collecting tears over the semester and pouring it over the stage, like, and hoping it's one of those like little magic books that kids get with like the pen. It's water pen, and you write it with the water pen, and it reveals the picture. You guys know what I'm talking about? Have you guys ever had one of those? Phoenix had one, and he enjoyed it for a little bit. Short-lived, but either way, we could do that. We could cry over it and see if that does anything, but that's not going to work. It's not going to work. I don't have I'm not spending that much money on you guys. I'm sorry. I can't make 8 pages that do that. That's way too much money. I'm already at my printing budget limit. So I make my exams multiple pages because I have the redo on the backside. So what would you do? Pull out the -1 to the k. That's definitely an option. And then what else would you do? So which test? The root test? And I'm glad someone mentioned it. I'm glad someone mentioned it. In its current format, the root test or the ratio test is going to be a moot point because it's not a product of things right now. It's a sum of things. So the root test doesn't work through that. Remember, just so like I'm going to write it fading because I don't want you writing this down. The nth root of a plus b does not equal the nth root of a plus the nth root of b. So we run into a problem. One solution would be to find a common denominator. And that is one way to do it. Find a common denominator, then do the root test or the ratio test and see what happens. And it will work out. But there's actually a more clever way. This thing right here, you can verify it on your own time. It has a radius of convergence of 2. And it also has an interval of convergence of bracket. Wait. I plug in -2, it diverges. If I plug in 2, it diverges. It has a radius convergence of -2 to 2. And the green one, you can do the same thing. You can do the root test or the ratio test. It doesn't matter. And you'll find out that this one has a radius of convergence equal to 1/2 and an IOC of -1/2 to +1/2. So, and this is a very common thing that we do later on in mathematics, is in order for these things to converge, both of them need to converge, right? There's no other way. Because even though the blue converges at 1, the green doesn't. So if you're looking at this as a series, basically what's going to happen is if you plug in 1, this thing is going to converge, but this thing is going to diverge, and the whole thing diverges. So you need to find the intersection, is what we call it, the intersection of the two. So that's the faster way to do it. Option 1, the long way, which I'll just write out. This would be the way that I would probably think of if I was on an exam and I couldn't figure it out. If I had a stroke of genius, awesome. That's always a great feeling when you have that happen. Unless it's in the last minute of an exam, which is always stressful because then you start getting a rug burn on your or friction burn on your pinky when you're writing. Speaking from experience, but I don't expect us to have that stroke of genius every time. Just like, oh, that makes sense. Doesn't always happen. So the long way is to find a common denominator in this segment right here and ratio or root test. Bleh. That'll take way too long. It can work. It's going to be sticky. I mean, it's going to be not too nice. I mean, nicer than most things, but there's going to be a lot of hand weight, like a lot of minor calculus algebra that's going to be annoying. Option two is the clever way. Green has IOC -1/2 to +1/2, and blue has IOC -2 to 2. Since we need both to converge, we need the smaller of the two. So the IOC is parentheses -1/2 to +1/2. And I encourage you, while you're on your own time at some point, to definitely go through and check this out, see if it and try it the long way and see if you get the same answer. If you plug in -1/2, that piece converges and that piece diverges. So it will not converge at either endpoint. But you can verify it if you want. So it's kind of a situation. This new series, this power series, it has its hands tied. It has to satisfy both of them. And since this interval is contained within this interval, it has to go to the -1/2 to the +1/2. Any questions on that? Okay, let's go ahead and take our break, and we'll come back at 11:09. People watching the recording, go get some fresh air. All right, so we're back, and so once again, we're not going to have 4.4 represents Taylor series will not be covered on the final exam, but I do want to mention the two different Taylor series formulas for that we're just going to add to our notes. So some known Taylor series. So if you have y equals sine of x, that equals the sum from k equals 0 to infinity of -1 to the k, x to the 2k plus 1 over 2k plus 1 factorial. That'll work because it'll be 1 minus x. No, it'll be plug in 0, you get x minus x cubed over 3 factorial. Yep, that's good. That is the known series representation of sine. That works for any value of x. The radius of convergence, which you can verify in your own time if you want, it has radius convergence of -infinity to +infinity. So this is a representation of sine everywhere. Cosine is going to equal the sum from k equals 0 to infinity of -1 to the k, x to the 2k over 2k factorial. And that also, which you can prove on your own time, that also has a radius convergence of -infinity to +infinity. And last but not least, the other one that we already talked about, but y equals e to the x equals the sum from k equals 1 to infinity of 1 over n factorial times x to the n. Now I want to show you something really cool called Euler's identity. Has anybody heard of it? If you haven't, It's a very, very unique fact in mathematics. And so we're going to take a complex detour. So we all know that I is equal to the square root of -1, right? I is the square root of -1. It's the only, it's defined as the complex number that's the solution to the polynomial equation x squared plus 1 is equal to 0. I squared is equal to -1 because if you square them together, you get -1. That's kind of how it's defined. Some people define it as square root of -1. Other people define I as the number whose square is equal to a negative number. Then, if you do I cubed, you end up with I squared times I, which is -I. And if you do I to the fourth, that's I squared times I squared, which is -1 times -1, which is +1. Okay? And then it's cyclic. I is a cyclic value, right? If I do I to the fifth, that'll get I to the first power. I to the sixth is -1. I to the seventh is -I, and I to the eighth is equal to +1, etc. So every 4, it repeats itself. And if the remainder you get when dividing your exponent by 4 is 1, you will get I as the number. If you get a remainder of 2, it'll be -1. If you get a remainder of 3, it'll be -I. And if you get a remainder of 0, it will be 1. So for example, I to the 107 is, so I'll do 107 divided by 4. 4 goes into it 2 times. We get 8, subtract 2, 7. Not 7, but 6, right? 24, yeah. 24. And we get a remainder of 3. Implies that this is equal to -I. You can also do it a different way. You can break it up into I to the 104, which is just a bunch of I to the fourths times an I cubed. But just as a fun little aside about complex numbers, and I bring that up, it's cyclic. We know another type of function that's cyclic, trig functions. They are periodic. And so here's a fun little fact. E to the I pi, or e to the I x, rather. So this is a weird thing. You can do this if you extend yourself to complex numbers. Complex numbers can be plugged into functions. These become complex functions, meaning that they are 4-dimensional. They take in 2 inputs, a real input and a complex input, an imaginary input usually is what we call it, and they spit out another complex number that is a real input and a complex input. That is 4 variables total. So this makes a 4-dimensional function. So it's hard to visualize. We can't visualize it too well. There are ways that we have done it as mathematicians to visualize what happens, where we look at it in 3 dimensions and then we add an extra layer of color hue to decide what it looks like. So if you ever look at a complex analysis book, you'll see a lot of pictures of surfaces in 3 space that have different shadings between red, blue, and green. And that's kind of how we decide to look at them. That's the best we've got. But anyways, so now that we've done that complex aside, by definition, this is equal to the sum from k equals 0 to infinity of ix to the n over n factorial. Right? I just plug that into the e to the x function. Its power series is that. And then let's just go ahead and write out a few of the terms. When k is 0, or sorry, I should write n, excuse me. When n is 0, it's just going to be 1. When n is 1, it's going to be plus ix over 1 factorial. Then it's going to be I squared x squared over 2 factorial. And then it's going to be plus I cubed x cubed over 3 factorial plus I to the fourth x to the fourth over 4 factorial plus dot, 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 on and on forever. Right? All cool with that so far? Hope this is interesting to you. This is really, really fascinating to me. So we know that I squared is equal to -1. This is equal to -I, and this is just equal to 1, right? Because I to the fourth, I cubed, and I squared. So what this equals is 1 plus ix minus I squared, x squared over 2 factorial plus I times x cubed over 3 factorial plus x to the fourth over 4 factorial. And I can, in fact, continue this on for us. The next one's going to be I to the fifth, but that has a remainder of 1 once you divide it by 4. So it's going to be plus, minus right here, minus right here. I got ahead of myself. I wrote it up here, but then I read it as a plus. It's a minus. Then it's going to be plus I x to the fifth over 5 factorial minus x to the sixth over 6 factorial plus plus minus, and so on and so forth. So it goes positive, positive, negative, negative, positive, positive, negative, negative, positive, positive, negative, negative. It keeps alternating like that, right? And there's a theorem in upper division mathematics which says that you can jumble things around however you really want in the series. It's a really, really annoying thing, but you can do that. So what I'm going to do instead, which ones have the i's? All the odd powers of x. And all the even powers of x don't have anything. So this is equal to, parentheses, 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus dot, 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 plus I times, I'm going to factor out the I from all of those infinite terms. And the reason why I can do this, by the way, sorry, this is just the mathematician in me, just trying to make sure that I am covering all my bases. I can do this, I can factor these things and rearrange them because the interval convergence for E is everything. The whole, we're working in the complex plane now, and the complex plane is no longer a line, but it is a grid. And it has interval of convergence for everything. We just saw it, the radius convergence. It didn't matter that we were only working with real numbers. It extends beyond that. And so this thing converges for all real, or for any value. And because of that, this is why I can factor out the I from an infinite number of terms. That is only allowable in certain contexts. So that's just something we have to be appreciative of. And then we've got x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus dot, 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 on forever. Now, if you were to write this as a series, that's all the even integers. This is equal to the sum from k equals 0 to infinity of -1 to the k, x to the 2k over 2k factorial. And then this is I times the sum from k equals 0 to infinity of all the odd powers, which we know, which we learned, all odd numbers can be either written as 2k plus 1 or 2k minus 1, depending on the situation. Here, it's going to be 2k plus 1. So it's -1 to the k. It has to alternate x to the 2k plus 1 over 2k plus 1 factorial. But what is that? That's cosine and sine. So we have a very, very famous formula. This is Euler's identity. E to the I, usually write it as a theta, is equal to cosine of theta plus I sine of theta. Isn't that miraculous? You can write an exponential function in terms of a sum of of two trig functions. That is bizarre to the nth degree. That's why complex analysis is very cool, by the way. That's the thing that I study in my own free time with mathematics is complex analysis because it is where all the cool kids are at. True story. If you go to any math department, if you plan on transferring to UNLV or you plan on transferring to any other college, you go to the math department, look for the people who have the complex analyst next to their names, and you'll see that they just look way cooler than everyone else. If you look for the algebraists, they're the people who have the crazy hair and they hate everybody. So it's a true story. Algebraists are just weird. And and then real analysts, they're weird people as well. We're all weird. You don't go into a math degree without being weird. But either way, and so there's the famous version. E to the I pi would equal cosine of pi plus I sine of pi. But sine of pi is 0. And cosine of pi is -1. So we have e to the I pi plus 1 is equal to 0. That is one of the most famous equations in all of mathematics. And the reason for it, if you've ever heard a mathematician gush about it and say, oh, it's so cool, realize this involves the most infamous complex number of all time, I. It involves one of the two most important irrational numbers, e and pi. It contains the multiplicative identity, 1, and it contains the additive identity, 0. It has so many of the core elements of all of mathematics. So I think this is pretty freaking nifty. And it shows up a lot more than you'd think. And this actually, if you plan on studying complex analysis, this fact is quite important, actually, about when it comes to understanding what E looks like in a complex plane. So, cool fact. Any questions on that? So now you can actually show that to people, and it looks really, really strange. It looks really like people think you're joshing them. They think you're lying. Nope, there's a proof of it, and now you have the proof. You can show them it, and they'll still won't believe you. They still won't believe you. So that's ridiculous. But you can't reason with those types of people. And so you just find the cool kids, complex analysts. Okay, so with the remainder of the time, so that's all I really wanted to show about Taylor's series is those three important series. And then the fun fact about Euler's identity that is so unique. And then the rest of the time, I just wanted to do 2 or 3 extra problems, just some good practice on radii of convergence. Because normally, if you've looked at our calendar, when we finished Unit 1, we had a day of practice on Unit 1. When we finished Unit 2, we had a day of practice on Unit 2. When we finished Unit 3, we had a day of practice on Unit 3. When we finished Unit 4, let's have a little bit of practice. Let's do 2 or 3 of these guys. So find the ROC, find the center, ROC, and IOC of A, which will be, someone pick a letter between F, G, H, and K. G, excellent. G of X is equal to the sum from n equals 1 to infinity of n squared x to the n over 2 times 4 times 6 times ... times 2n. He chose the hard one. Not really hard. It's just, and remember, that's not 2n factorial because that 2n factorial includes all the odd numbers as well. 2n factorial would be 2n times 2n minus 1 times 2n minus 2 times 2n minus 3 all the way down to 1. This is just all the even numbers. And then B, so a letter F, H, or K. F, okay. F of X is equal to the sum from n equals 1 to infinity of x to the n over n. Well, let's change it up. Let's make sure it has a different center. X plus 2 to the n, like that. So it's x plus 2 to the n over n times 3 to the n, right? N equals 1 to infinity. So go ahead and start working through those. I'm going to pause the recording. I think you should all work through them and see what you get. Okay, so I did hand back your exams for exam 3. You have until next Tuesday to turn in the redos. Please make sure everything adds up correctly. If it doesn't, let me know, and I'm happy to look into it and see what I can fix. Unless it's higher than the score that you're supposed to get, don't let me know. But one thing I wanted to mention, specifically on the last problem, a lot of people were trying to compare the decreasing by showing that a sub k plus 1 is less than or equal to a sub k. The problem with that one is that the numerator is getting bigger at the same time. The numerator and the denominator are getting bigger at the same time. The numerator is getting bigger slower than the denominator, so that is a good thing, but it's not guaranteeing that it is a decreasing sequence. You'll need to do something else. I don't think anybody actually showed that it was decreasing properly. I can't remember. And it's okay. It happens. But you need to do something else to prove that it's actually decreasing for all k values past 2. It's quite quick. It's not too terrible once you get started with it, okay? I was also thinking there are 2 options on questions 3 and 4, aren't there? How about 1 point of extra credit if you do those options that you didn't do? Okay? 1 point of extra credit for the problems that you didn't do. So if you did option A, you can also do option B for up to 1 point of extra credit, meaning you can get 50% of the points back plus 2, as long as you do it correctly. Okay? So that's that. And then if you think I don't think I said it, but I think if you think anything was graded unfairly, please come up and talk to me either before class, after class, or my office hours. I'm happy to go through it. It could be that I graded it too harshly. It happens every once in a while. So no one else is going to advocate in the class for you besides yourself. So if you think you deserve more points, come up and talk to me. The worst thing I'll say is no, right? Okay. So back to working on it and stuff, and you can also look at your notes. Like you can look through your exams too if you want. Okay, so the first one has a center at 0 because it's just x to the n. So because it's dealing with a pseudo factorial, my recommendation would be the ratio test, because trying to do the root test, it doesn't really work out too well. So ratio test, then the n plus 1th term goes up top, and what that would be is n plus 1 squared times x to the n plus 1 over 2 times 4 times 6 all the way up to 2n, and then 2 times the quantity n plus 1, which is 2n plus 2. That's the next term in the sequence. And then over a sub n, which is n squared x to the n over 2 times 4 times 6 all the way up to 2n. Excuse me. Every one of the even numbers except for 2n plus 2 cancels. So, and then all the x's cancel except for one of them. So what we end up with is the absolute value of x. And then up top, we've got n plus 1 squared, but that becomes n squared plus 2n plus 1. And then you've still got an n squared in addition to that 2n plus 2 in the denominator. So that's really 2n cubed plus 2n squared. So the numerator has a lower degree. So no matter what x is, even if x is 10 billion, the limit as n approaches positive infinity, that'll be just 10 billion n squared over 2n cubed, which will go to 0. So no matter what x is, this value will always be strictly less than 1, which means that the raised convergence is infinity, because any x can be plugged in and it will be less than 1. The ratio on the root test, if the value is less than 1, it converges. And because it converges to 0, no matter what x is, it means that it's the whole real line. So the interval convergence is negative infinity to positive infinity. Are there any questions on that? Part B, the center is x equals -2 because it's x plus 2, but power series are written as x minus x sub 0. So that's why the center is -2. And I decided to use the root test, but the ratio test will work out fine here as well. And the fact of the matter is you've got x plus 2 to the n to the 1 over n. Those cancel. We're just left with an absolute value of x plus 2. And then we've got the nth root of n times 3 to the n to the 1 over n. The 1 over n and n cancel. We've got 3. And then by our special limits that we know, the nth root of n goes to 1. And in order for this to converge as a series, we need this to be strictly less than 1. So solving this, I multiply by 3 to both sides, and that gives me the radius of convergence. The radius of convergence is 3. Then I need to find the interval of convergence, which I do by first finding the open interval of convergence, at which I will subtract 2 from both sides to get the open interval of convergence to be -5 to 1. I'll plug in the endpoints to see whether or not they can be included. -5, when you include that, you get -1 to the n over n, which is convergent by the alternating series test. But if you plug in +1, you get 3 to the n over n times 3 to the n. The 3 to the n's cancel, and we have the harmonic series, which is divergent. You can either say divergent because harmonic series, or you can say divergent by the p test, because the p value is 1, and it will diverge if p is less than or equal to 1. So you can include the left endpoint, you have to exclude the right endpoint. So it's bracket -5 to 1 parenthesis. Any questions on those? We feel like if on the final exam there's a power series problem, we can figure it out? Think so? Hope so. I wouldn't be surprised. I wouldn't put it past them. I can't say for certain. I don't know. I haven't seen the exam yet. They wait until week 14 to hand out, as you might imagine, to make sure it's all fair for everybody. But I wouldn't be surprised as a teacher, speaking as a student, right? This is something we've been doing for about 2-3 weeks. It's probably going to have at least one question on it. That's a fair game thing. Whether it's trying to integrate or differentiate, or just finding a power series representation, or just finding radius of convergence and interval convergence, that's up for interpretation. But yeah, that'll do it for today. We'll pick up next time on Thursday with Unit 5, which is on parametric equations. So that's what we'll pick up with. You'll see I'll send out the notes for 5.1 pretty soon, okay? Otherwise, have a great rest of your day. The exam redos are due on Tuesday of next week. So spend some time looking at it and getting some points back. And remember that you can do the other option of questions 3 and 4 for up to 1 point of extra credit on each. So you can get 50% of the points back plus an additional 2. All right. Have a great rest of your day.